Hello.
Hello, nice to see you. Hello, everyone.
Good afternoon.
Good afternoon.
Good afternoon.
Good afternoon. Hi. So, hello. So far we were talking during our discussions on how external magnetic field effects, like moving charges or electric current in conductors. But also we need to highlight that moving charges or current in conductors also creates magnetic field around these conductors. So today we are going to discuss how to calculate magnetic field, which is created by electric current in conductors, and we'll consider a few examples how we can calculate magnetic field next to different configurations of conductors with electric current. Let me switch to our slides. So to be more specific, so this relationship of magnetic field on like magnetic field with the electric current is governed by so-called Biot and Savart Law, and it was found experimentally, like several features of magnetic field, which is formed next to conductors with electric current. So if we consider some small length element of a conductor, so let's consider some conductor. We have some length element, which could be represented with ds vector. So magnetic field vector, which is created by this length element of a conductor with current, we can mark it as dB vector in some point in space around this conductor. Was shown the following relationship. So first, magnetic field vector dB is perpendicular always to this length element vector, and also unit vector r, so it also perpendicular to magnetic field. This unit vector defines direction, which connects the length element ds with the point in space where we want to know magnetic field. So the magnitude of magnetic field, so we can write dB, absolute value, is inversely proportional to 1 over r squared, which is distance from this length element to the point where we determine magnetic field. And also it is proportional to the we can write here dB vector absolute value is proportional to the magnitude of electric current which flows through the conductor, and absolute value of this ds vector length element. So the bigger length element, the larger magnetic field will be. Also, magnetic vector is proportional to the sinus theta. So we can write dB vector absolute value is proportional to sinus theta, where theta is the angle between ds vector and our unit vector, which defines the radius vector of this point position with respect to length element ds. So taking this into account, all these experimental findings, Biot and Savart developed this equation, which quantifies magnetic field next to a conductor with current. So in this case, we write like small magnetic field dB formed by a small length element ds. And that is given as follows. We have mu naught divided by 4 pi. These are some constants. Then we have electric current I. Then we have vector product of two vectors, ds times r unit vector. And this is divided by r squared, which is just distance between length element ds and point in space where we determine the magnetic field vector. So that is actually the Biot Savart law. Mu naught is permeability of free space, like magnetic permeability of free space, and that is equal to 4 pi 10 to the power of -7 Tesla times meter divided by ampere. So this is one of fundamental constants. And obviously, if we are talking not about some small length element and are interested in determining the net magnetic field vector created by a conductor of random shape with its edges at point A and B, then we obviously need to integrate and sum up contribution of small magnetic field vectors, which are created in given point of space around this conductor by each small segment, like length element of this conductor. So that means we need to deal with the following equation. So magnetic field vector, the net vector formed by all small elements of the length elements of the conductor will be equal to mu naught times I divided by 4 pi. These guys are constants, so we can take them out from the integral. So here we have integral of vector product ds vector R unit vector divided by R squared. So obviously we integrate over the length of all conduct. So in other words, we take this integral over the entire current distribution in this arbitrary shape conductor. So keeping this in mind, we can proceed with some examples which will help you to understand better how to apply Biot and Savart law and determine magnetic field next to conductors with current. Let us go to another slide and consider such a example. So let's start from a straight line of our conductor. So we have axis y and x. Let us assume that we have conductor with some current flowing through it in the direction along axis x. Some current I. Then we want to determine magnetic field in this point. Let's call it point P, created by this conductor with current. So we can pick up some small element, length element at coordinate x. Here will be the line which connects this small element, let's call it ds vector, which is oriented along the current. So this is our small element, this ds vector, and this is our r unit vector. This is unit vector which defines the direction from ds, small length element, to our point P, where we want to determine magnetic field. So the angle between axis y and this line which connects ds and point P will be some theta. So now let us figure out what will be the product, cross product of ds vector and unit vector r. So we can take actually absolute value of this product, ds vector r unit vector, and multiply it by k unit vector, which will be in the direction of axis z, which we don't show here, or in order not to make it too cluttered. So we know that the cross product of two vectors gives us a vector which is perpendicular to the plane defined by these two vectors, which are cross product. So the amplitude, like the magnitude of this cross product will be actually the magnitude of ds vector, and magnitude of ds vector, which is aligned along axis x, can be represented as dx, some small change of coordinate x, because it is aligned just along the axis x. And unit vector r is just magnitude is unity, so we just need to take into account orientation between these two vectors, means this angle between ds vector and r unit vector. So this angle will be pi over 2 minus theta. So keeping this in mind, we can write here that we have dx instead of like magnitude of ds vector. Magnitude of r unit vector is unity, so we don't have it. Then we need to put sinus angle between ds vector and r unit vector, and that is pi over 2 minus theta. This multiplied by k unit vector. It is possible to simplify this considering trigonometrical relationship. We can write that this will be equal dx times cosinus theta times k unit vector. So instead of sinus pi over 2 minus theta, we can write just cosinus theta. So in this case, we can, with this result, proceed already towards the determination of magnetic field vector, applying this Biot and Savart law. So dB vector, as was shown previously. So what we can write, we can also write here dB magnitude of this vector times k unit vector, since we already know the orientation of magnetic field from the product of ds vector and r vector, r unit vector. So this, according as we discussed previously, this should be equal to mu naught times I, electric current which flows through this conductor, divided by 4 pi. And here we have cross product ds r unit vector, so instead we can write just this. So it will be dx times cosinus theta divided by r squared, and here is our k unit vector. So now let us determine what will be r and how we can also represent this coordinate x. So in order to do this, we need to specify actually the position of this point P, and that position will be at the y coordinate equal to a. So that's this this height is defined by length a. So if we keep this in mind, we can already calculate what will be distance between small length element ds and point P. So this is r equal to a divided by cosinus theta. So we know this angle theta. So we can represent now distance r in terms of theta and a y coordinate of this point P. Also, we need to define this position x and this position x also in terms of theta. So that will be minus because it's negative. Here is origin of coordinates. So at this position it's negative coordinate minus a times tangent theta. So when we know x, we need to find the dx. So it's the differential. For that, we need to take differential of this expression, and dx will be equal to minus a d theta over cosinus square theta. So this is from the table which gives you rules for taking derivatives. We take derivative of tangent theta, we get 1 over cosinus square theta, and since it's differential, we multiply it by d theta. So once we have all this, actually these two terms, we can substitute them in our equation for magnetic field vector. So we substitute instead of r and dx. Let us do it. Maybe I can clean this part so we have it all on one slide here. So I can write that this is equal to minus mu naught times I divided by 4 pi times A yeah, that we will put later, just without. So then let's put substitute dx. So minus is here already. We will put a times d theta over cosinus square theta. And now we need to substitute for r squared. So that will be cosinus square theta divided by a square and multiply cosinus theta and times unit vector k. So now what do we have here? So we cancel out this and this. We cancel out this and this. So eventually we have minus mu naught times I divided by 4 pi times a cosinus theta d theta. Okay, so that is equal sorry, here is K unit vector, and that is equal to dB vector. Now, if we want to determine the net magnetic field vector at point P created not by just a single length element of this conductor, but by whole conductor. So what we need to do, we need to consider this conductor from one edge to another. And here will be some angle theta 1, and here will be some angle theta 2. So here we have independent variable theta. So we need to integrate from this expression for dB vector from theta 1 to theta 2. And that should give us the resultant magnetic field vector in point P. So let us do it on the next slide. So B vector will be equal to minus mu naught I divided by 4 pi A. Here we should not forget about this K unit vector, and integral from theta 1 to theta 2 times cosinus d theta, sorry, cosinus, so integral of cosinus theta d theta. When we take this integral, we will get, let's continue here, mu naught I 4 pi A, K unit vector. Here will be sinus theta from theta 1 to theta 2. Then we take into account this minus, so we can write mu naught I divided by 4 pi A sinus theta 1 minus sinus theta 2 and K unit vector. So this is the expression for the resultant net magnetic field vector in point P next to this conductor. So what is interesting here, let us consider some specific case. For instance, when we have very long conductor, so let's assume that position of left edge x1 is equal to minus infinity, like right edge x2 is equal to infinity, then this sinus theta 1 minus sinus theta 2 will be equal to sinus P over 2 minus sinus P minus P over 2, and that will be 1 minus minus unity equal to 2. So with this, we can actually write that magnetic field vector next to infinitely long straight conductor will be equal to mu naught times electric current I divided by 2 pi A. A is the distance from this infinitely long conductor to the point where we want to determine the magnetic field vector. By the way, here we should still have a unit vector since it's in the vector form. So now when we are done with the straight conductor, let us consider some curved conductor. So it will be this type of conductor, which is actually part of some segment of a circle. And in the center of this circle, let's consider our point P, where we want to determine magnetic field vector B. So let's pick up some point. Here will be vector ds, assuming that current is flowing in this direction along this conductor. Then we have unit vector r, which is pointed towards the center of this circle, and the radius of this circle is a. Here is also a. So the angle between the radius vectors of beginning and end of this current conductor segment will be theta. So now let us write the expression for magnetic field dB vector formed by some small length segment of this conductor. In this case, no matter which segment we choose, there will be right angle between ds vector and r unit vector. So keeping that in mind, we can write. So it will be mu naught divided by 4 pi times I. Then we have, we should have here vector product ds vector r unit vector, but we can just write here ds, like magnitude of this length element, because unit vector r magnitude is unity, and they have straight angle between each other. So there is pi over 2, sinus pi over 2 gives us unity, so we just don't write it. And here we need to divide by the distance between the length element and point P, where we determine magnetic field vector. So that is actually radius of this circle. So that is a squared. Now, no, without equal, we need to determine the net magnetic field vector. And in order to do that, as we know, we need to integrate. So B vector is equal to mu naught times I divided by 4 pi a square. These are constants because it doesn't change no matter how we move along this conductor. It is always at the distance a from the center of this circle. Then we have integral ds. So obviously, if we integrate over s, length element, all over the conductor, we will get just length of the conductor. So we can write mu naught I divided by 4 pi a square, and here I can put just capital S, which is the length of the conductor. How we can define it? If we know radius and this angle theta in steradians, we can write that the length of the conductor is equal to a radius times theta in steradians. So we can continue here. Will be mu naught times I over 4 pi a square times a times theta. So we cancel out this square and this a, and eventually we get mu naught I over 4 pi a times angle theta. So that is the expression for magnetic field vector. So actually here we put, so we did it for absolute value. So we can take away these vectors. But it also will be perpendicular to the basis defined by vectors ds vector and r unit vector. Will be also oriented perpendicular to the plane of our drawing. So now we also can consider, okay, what will be if this conductor actually is a circle conductor. So it does not occupy only a segment of this circle, but occupies this circle completely. So in that case, this theta, angle theta, will be equal to 2 pi. If it's equal to 2 pi, we can substitute it in this final equation. So we will get magnetic, like magnitude of magnetic field in the center of the circular conductor, like one coil, which is equal to mu naught I divided by, so what do we have, 4 pi here, a, and here will be 2 pi. So we can cancel these guys. Here will be 2. So we will get mu naught I divided by 2a. Mu naught times electric current, magnitude of electric current, divided by 2 radius of this coil, which will be filling completely this circle with a conductor which carries some current, electric current I. So with this, I would like to summarize our discussion today. And as I started at the beginning, so far we were considering how external magnetic field effects on mobile charges and electric current in conductors. However, there is if we go in opposite direction, we can consider mobile charges and current in conductors as a source of magnetic field. So it was shown experimentally. So if you have some electric current flowing through a conductor, you turn it, when you turn it on, it has some impact on permanent magnet placed next to this conductor. So for instance, if you have some compass, then this magnetized arrow of the compass will start to rearrange. Means that electric current creates magnetic field. So that was shown, and scientists Biot and Savart carried out a bunch of experiments which have shown us that magnetic field vector next to a small element, lens element conductor with current I can be given by this equation. So that is so-called Biot-Savart law, which means from here that magnetic field vector is always perpendicular to the basis formed by small lens element ds vector and radius unit vector r, which defines direction of the from the lens element ds towards the point where we want to determine magnetic field. And also it is reversely proportional to this distance between the point and lens element, like in second power, and directly proportional to the magnitude of electric current through the conductor. So if we obviously want to determine the resultant net magnetic field vector, we want to make one more step further and integrate it all over the given conductor configuration. Then it is possible to determine net magnetic field vector created by the whole conductor with electrical current flowing through it. Also, we discussed some experiments, some examples which give us better understanding how to apply this Biot-Savart law practically and determine magnetic field next to straight conductor and also curved conductor, which was considered as a segment of a circle. So with this, I would like to finish our discussion. And if you have any questions, you're welcome. So on Monday, we have day off. Actually, do you know, guys, we have, do we have lectures on Saturday for Monday?
I guess we still didn't get any message.
We didn't get what?
Any message on the
Okay.
mail.
Okay. Yeah.
One of my professors said that she received a message from Dr. Enns that said that we professors can use Saturday to have makeup lectures for Monday that they will miss.
Yeah, sure. Yeah, but I don't know. It's a bit tricky because I believe people are going to have some plans for Saturday. So I don't think that many will attend the lecture. Probably would be better that we don't disturb each other on Saturday. what do you think about it?
Actually, that's not a bad idea.
Yeah, I think that it will be okay to have some rest. So I send my greetings to all our girls. So we'll be soon there. Holiday, it's March. Be healthy and pretty. And hope you will, all of you guys will enjoy this short holiday season for a few days. Enjoy some free time and gain some energy for the rest of this semester. Don't forget physics also. Maybe you can have some time to spend to solve some problems or go through the textbook on some questions which you don't understand. Then we will see each other next time on Wednesday, if I'm not mistaken. And we'll continue our lecture course further. Okay, then have a good evening and these days off. Take care and see you on Wednesday.
Thank you very much.
Thank you.
Thank you
Goodbye.
very much.
Thank you.
Goodbye.
Bye.